To the class. Dear students, today we are going to see benzyne mechanism, nucleophilic aromatic substitution reaction through benzyne intermediate. Okay, so we will see. So what here we are going to see is what is a normal route of nucleophilic aromatic substitution, the normal route, and in which situations does it take the benzyne intermediate route, and what is the difference between the normal route and the benzyne intermediate route for the same mechanism. And then we will look into the reaction and the mechanism. So let us start nucleophilic aromatic substitution reaction through benzyne intermediate, or simply the benzyne mechanism. Let us start this. So normally benzene undergoes electrophilic aromatic substitution reaction. You know, the characteristic reaction of benzene is electrophilic aromatic substitution reaction. But in certain conditions, it does show nucleophilic aromatic substitution reactions. In what condition will it show nucleophilic aromatic substitution reaction? There are two conditions. Number one, if an electron withdrawing group is attached to benzene, a strong electron withdrawing group. A strong electron withdrawing group is the NO2 group, or it can be an aldehyde group or a ketone group. Along with this condition, there is one more condition. The second condition is a very good leaving group should be attached to benzene. A very good leaving group should be attached to benzene. See, if a strong electron withdrawing group is present in benzene ring, consider this example. This is 1, 2, 4 dinitrobenzene. So consider this example. This is a very strong electron withdrawing group present here. Here also it's a strong electron withdrawing group. Now it will withdraw the electrons of the benzene, correct? And that will lead to a positive charge in benzene, and any nucleophile can come and attack benzene. So this is the condition of your nucleophilic aromatic substitution reaction in benzene ring. What are the conditions? There are two conditions. One, a strong electron withdrawing group should be present in benzene. Number two, a very good leaving group should be linked to benzene. So the strongest electron withdrawing group is the NO2 group. Okay, it is attached and two are attached. Okay, and the best leaving groups are halogens. So we have attached a halogen here. Now let us see what happens when nucleophilic aromatic substitution takes place in 1,2,4 dinitrobenzene. So what happens here, because as you can see, the nitrogen lone pair has been donated here to phenyl ring. It is positive in nature. Two electronegative atoms are already there. They are pulling the electron. Nitrogen itself pulls the electron, and now this pair of electron comes here, correct? And with the result, when this pair of electron comes here, this pair of electron goes there and a positive charge comes here, correct? So now we have achieved, this is a carbocation. Okay, this is a carbocation. Now let us subject this carbocation to a nucleophile. The nucleophile attacks at the positively charged carbon atom like this. So this step in nucleophilic aromatic substitution is the first step, which is called as the addition of nucleophile. Nucleophile has added to positively charged carbon atom. Positively charged carbon atom. The second step in nucleophilic aromatic substitution is elimination of leaving group. What would happen? This is very unstable condition. It would come back here as a pair. When it comes back here as a pair, this pair of electron comes back here. When this pair of electron comes back here, this Cl minus, it goes. So what is the net result? The net result is the elimination of the leaving group. Cl minus, when it is a very stable anion, right? When chlorine is not so stable, but Cl minus is stable, because Cl minus is having the configuration of argon, which is inert gas. So it wants to be Cl minus. Cl actually wants to withdraw electron, and it wants to become Cl minus so that it can become stable and it can have an electronic configuration of argon. It wants to do that from the beginning, but there was no, the conditions were not apt. When we subjected it to a nucleophile attack, okay, when we subjected it to a nucleophilic attack, and when these NO2 groups were present, when the conditions were set, then chlorine left with an electron pair, and in its place nucleophile, which is a not so good leaving group and much better base, it came and attached to the aromatic ring. This is what has happened. So normal nucleophilic aromatic substitution, normal, not the benzyne. Normally this is what is taking place. Normally the route is addition of nucleophile and after that elimination of leaving group. So it's a addition elimination route. Normal nucleophilic aromatic substitution reaction is a addition elimination route. The thing here to note that is only one product like this is formed. The product of normal nucleophilic aromatic substitution reaction is only one product. In this product, the nucleophile is attached to carbon, which was initially attached to chlorine. The nucleophile which is attached to carbon, which was initially attached to the leaving group. So only one and one product is formed if the course follows addition elimination route of nucleophilic aromatic substitution reaction. Only one product is formed if it follows this route, addition elimination route of nucleophilic aromatic substitution reaction. Only one product is formed. Please note this down. Now, very few reactions can proceed through another route. That route is called as the benzyne route, benzyne mechanism. Okay. Very few reactions can proceed through another route. That route is called as the benzyne mechanism. So what happens in benzyne mechanism? Let us see. So for this I am taking chlorobenzene. I am going to treat it with nucleophile NH2. I can get it from soda amide NH2, and I treat it in dilute ammonia and minus 33 degrees Celsius. What would I get? I would get this, and I will also get this. What is the difference between the two? Do tell me. And of course Cl will go with and NaCl will be formed. That's not important. What is important is we get this is also nucleophilic aromatic substitution reaction, but this reaction is not the normal addition elimination type. It is not normal addition elimination type. If it was addition elimination type, then only one product would have been formed. This is not that. This is through another mechanism, and in this mechanism what happens, it results in formation of two products. I know it is one product, but it results in formation of two products. What is the difference between them? The two product is, the first one is where the nucleophile is attached to carbon, which was earlier attached to leaving group, and the second product is where the nucleophile is attached to carbon adjacent to the carbon, which was linked to leaving group. So in these very few types of reaction, like I said, reaction that proceed through another route, not the typical addition elimination route, not that route, but the reaction that proceeds through the benzyne route, what happens is two products are formed. In the first product, the nucleophile is attached to the carbon, which was earlier attached to your leaving group, and in the second product is where the nucleophile is attached to carbon adjacent to the carbon, which was earlier attached to the leaving group. So two kinds of products are formed. So how will you, and that too in a 50-50 proportion, 50:50 proportion. That means 50% of this product is formed and 50% of this product is formed. Had there been a CS3 group here as a primary substituent, had it been orthochlorotoluene, okay, had there been a CS3 group here as a primary substituent, then we would have got two products, right? One would have been the orthoisomer, the other would have been a meta-isomer. Correct? So 2 and 2 products are formed had there been a primary substituent linked to your chlorobenzene. So what explains that too in 50:50 proportion? So what explains the formation of two different kinds of products in 50:50 proportion. The only explanation is given if we justify this reaction by formation of intermediate, which is benzyne intermediate. Actually, what happens? Such kinds of reaction, it proceeds through benzyne intermediate. This is the benzyne intermediate. To understand what I have said now, this kind of reaction, that is 50:50 product, can only be formed if there is a benzyne intermediate. What is the reality of benzyne intermediate? What are the features? Let us see. The benzyne intermediate, especially this side, this side is very strained. The benzyne intermediate is very strained. The benzyne ring is actually having very big strain. The benzyne ring is having a strain of 50 kilocalorie per mole. 50 kilocalorie per mole. Do you know what is the strain in cyclopropane ring? Cyclopropane ring is having strain of 28 kilocalorie per mole. So according to their strain, cyclopropane is the most unstable ring, right? Here we are seeing that benzyne is more unstable than cyclopropane. It is very unstable. Very unstable. That means the ring can break. And the triple bond here is actually very weak. The triple bond here is very weak. How do we prove? To understand why the triple bond is very weak, we have to understand the molecular orbital picture of benzyne. So let us see the molecular orbital picture of benzyne. Then we will understand why the triple bond is weak. So this is the situation. This is the carbon. All these, there are 6 carbon atoms. Out of these, only these 2 carbon atoms are sp hybridized. Rest all are sp2 hybridized because there is double bond. Only these two carbons are sp hybridized. Correct? sp hybridized means there are 2 sp orbitals. 2 sp orbitals, as you can see here. Right? These are the 2 sp orbitals which are involved in double bond formation. This is a sigma bond and there are 2 pi bonds. Now look at this benzyne. If double bond is to come, they have to overlap. Correct? But these sp orbitals, they are far away from each other. They are facing against each other. They are not facing towards each other. Right? They are facing themselves away from each other. So effective overlap here won't take place. It won't show any kind of effective overlap. It will show overlap definitely, but that overlap will be very ineffective. Okay, very partial overlap will take place. So that is why the triple bond that is formed, because they are facing away from each other, they won't show effective overlap. Therefore, the triple bond that is formed is also weak. Weak in the means that it can break at any time. Okay. So that is why benzyne is very fragile. It's a very short-lived intermediate because the triple bond can break at any time. Such is the fragility of the triple bond that the benzyne intermediate, it exists as 3 resonating structure. It exists in 3 resonating structure. Let us see the first resonating structure. This is the first one. See here. Suppose if the triple bond breaks, okay, the upper lobe takes the pair of electron. If the triple bond is breaking, then one of the lobe here, the upper lobe here, suppose it has taken a pair of electron, then of course the lower lobe is positively charged. And then a structure exists when actual overlap takes place. Right? And then again a structure exists where the lower lobe takes the pair of electron. Now here the lower lobe takes the pair of electron. This is a double bond here. Yeah. Yes. So these are the 3 resonating structures of benzyne. 3 resonating structures of benzyne. So benzyne exists in these 3 resonating structures because this triple bond is so fragile, it can break at any time. when it breaks, it can be a case, two cases can come. In the first case, the upper lobe takes away the pair of electron and the lower lobe gets none. In the second case, the lower lobe takes the pair of electron, the upper lobe takes none. Now, if a nucleophile is to attack, NH2 is to attack, where it would attack? A nucleophile is to attack, if it is to attack, where it would attack? Here, in this case, it would attack the lower lobe. Okay, so that would result in this structure, right, and negative charge here. Or the nucleophile can attack at the upper lobe, and that would result in this structure, and negative charge would come here, right? So it would result in two products like we discussed earlier. If the reaction, if nucleophilic aromatic substitution, if this reaction proceeds through benzyne intermediate or benzyne route, if it proceeds through benzyne intermediate, then two products will be formed. I said it when we started the class. In the first is the case where the nucleophile is attached to carbon which was initially attached to the leaving group. This is that structure. And the second product will be in which the nucleophile is attached to the carbon which is adjacent to the carbon which was initially attached to halogen. This is that structure. Now suppose here the benzyne, here there was a primary substituent. If it was a primary substituent, then what would have been the result? Yes, two products would have been formed, right? If there was a primary substituent, right? Then two products would have been formed. The first would have been a meta isomer and the second would have been an ortho isomer. So two isomers would have been formed if a primary substituent was attached. So this is the importance of the reaction proceeding through the benzyne intermediate. If it proceeds through benzyne intermediate, there is no doubt that two products will be formed, and that too in equal proportion, because there is equal probability of the electron going towards the upper lobe and into the lower lobe. Now let us look at the mechanism of this reaction, but before understanding mechanism, let us once again look the reaction. Let us look at the reaction what we have seen here. So this was the reaction we were talking about. It is treating with suppose we are taking bromobenzene here and we are treating it with soda amide, and then we are using dilute ammonia. You don't need to give temperature, minus 33 degrees Celsius is enough. Rapidly aniline is formed at a rapid rate. So this is the aniline formed at a rapid rate, and of course there is another aniline formed which is the you can say this aniline, and both the anilines are formed at a very rapid rate. So of course there is NaBr also formed. So 2 aniline, so I can write it as 1. So 2 aniline, what I want to show here is that here there are two kinds of aniline formed. Here the nucleophile is attached to carbon which was initially attached to the leaving group, and here the nucleophile is attached to the carbon which is adjacent to the carbon which was attached to the leaving group. Two kinds of anilines and two kinds of carbons it is getting attached to. Let us now look how it is happening. Mechanism. In mechanism we have already seen how benzyne intermediate, after the formation of benzyne intermediate, how two products are formed. Already we have got an idea. Let's see, in this mechanism we will come to know how benzyne is formed. So let us see the mechanism. The mechanism is nucleophilic aromatic substitution via benzyne intermediate, or simply the benzyne mechanism. Two steps are there. Step number one, formation of benzyne intermediate. Formation of benzyne intermediate. Let us see how benzyne intermediate is formed. So we have got the chlorobenzene like this, right? So this is chlorobenzene, Here also there is H. Actually everyone is having H. All carbon atoms are having H. I am writing the H here so as to understand the mechanism. Now let us react it with soda amide. Of course nitrogen is having lone pair. This is negative and this is positive. There is a pair of electron extra that it takes from sodium, and sodium dissociates, correct? And NH2, it acts as a very strong base. It would knock out a H here from here. So the result would be this thing, chlorine and minus, right? And there you go. That would be the net result. Now what would happen? This electron pair would come here and chlorine may go. So that would result in your benzyne. So there goes your benzyne. What has happened here? The amide group, soda amide, it is acting as base. It is acting as a base. We have seen dilute ammonia is also used at minus 33 degrees Celsius. We are not now looking at dilute ammonia's role. We are just looking at soda amide's role here. Soda amide is not the nucleophile. Soda amide acts as a base. So it knocks out H. When it knocks out H, the pair is left here. This pair now comes here as one more bond which forms the triple bond, and Cl minus goes. Cl minus of course wants to go, so it will go. And now we get a benzyne ring. Okay, so this is an intermediate, a very short-lived intermediate. Let us see what happens to the short-lived intermediate in the second step. Step number 2, nucleophilic aromatic substitution. Aromatic substitution. Let's see what happens in this. So let's talk about the benzyne intermediate here. This is the benzyne intermediate. Right? Now I have said it has two structures. In the first structure, the above lobe, the lobe that is above, it gets the pair of electron, and the lobe that is below gets positive sign, right? In the second structure, the lobe that is below gets negative sign and lobe that is above gets positive sign, right? Now both these structures can be affected. Now comes the role of dilute ammonia. So dilute ammonia, I am writing it like this. Now there is a pair of electron here. It can get attracted to positive, right? And here it can get attracted to the upper lobe here. So two structures can come. One structure is like this, right? And the double bond is like this. And here the second structure is like this, NH2H would come here. So two structures can come. If it attacks the positively charged lower lobe, then of course nucleophile will come here, and if it attacks the positively charged upper lobe, then the nucleophile comes at the upper lobe, right? So now let us see what would happen. So now what can happen, your H, it can go here. This is called as internal proton transfer. H can go here, right? And this can come here as pair and remove this positive sign. Here also there is a pull of electron here at this side. When it pulls the electron towards itself, H plus goes and comes here. So the net result here are two structures, NH2 here and NH2 there. So we get two products now, one in which this one, right, one in which the nucleophile is attached to carbon which was initially attached to chlorine, and the second structure is nucleophile is attached to carbon atom which is adjacent to the carbon atom which was earlier linked to chlorine or the leaving group. Now if there is a CH3 group here as primary substituent, if we were talking about that, then we would have got two isomers. One is the ortho isomer and the other is the meta isomer in a 50:50 proportion. There is no para isomer. No para isomer is formed. Dear students, this is what happens when your nucleophilic aromatic substitution proceeds through the benzyne route, proceeds through benzyne intermediate. Normally it won't happen. Usually it takes the addition elimination route where only one product is formed. This happens in rare cases, in some examples only, where there are two products formed. One, the ortho isomer, and the other, the meta isomer in a 50:50 proportion. If a reaction shows like this, then it means that the nucleophilic aromatic substitution has proceeded through the benzyne route. Dear students, I hope you have understood the class and you have liked the same. If you have done so, if it is valuable for you, please do not forget to subscribe the channel, do like it and share it with your friends. Thank you very much.